So this will be the last section of our Chapter 18 notes, the last problem we'll look at, and that is diffusion and chemical reaction inside a porous catalyst. And it will illustrate a, a different aspect of modeling of mass transport than we've seen before, and this is the effective averaging approach. And so, as you may well know, heterogeneous catalysts are widely used to enhance and in fact enable rates of chemical reaction in a wide variety of industrial processes. Often these catalysts are dispersed or distributed inside and on the surface of high surface area porous particles to maximize the contact area of the catalyst with the surrounding fluid. And so a spherical particle is shown here, and kind of a schematic blow-up of it shows pores, and the catalyst is deposited on the walls inside these pores, and a chemical reaction occurs inside the catalyst. And so the general picture here is that a reactant A, which is present in the fluid outside the catalyst, will diffuse perhaps through a boundary layer and then into the porous structure of the catalyst particle, where it undergoes reaction to form B, and then B will diffuse out and away from the catalyst particle under the influence of concentration gradient. And the in a typical reactor, it would contain many of these particles, and we have a gas stream of A flowing around the particle, and A converts to B at the gas-solid interface. And we'll take the concentrations of A and B right at in the gas phase, but just at the outer edge of the particle, to be CAR and CB at R respectively. And so to analyze the mass transfer inside this catalyst particle, we don't attempt to solve the detailed mass balance or flux equations inside this tortuous pathway. Rather, we use the 1D equations and use appropriate averages for the diffusion coefficients that takes into account the tortuosity and porosity of the catalyst particle. I'll show you how we do that here in a moment. And so then the flux and diffusion coefficients are always interpreted as effective or average values. These will not be diffusion coefficients that are material properties of the species that are in the mixture, and so that they'll be dependent on the species, but also on the tortuosity and porosity of the catalyst particles. And so we begin by writing a shell balance on the thin spherical shell inside the catalyst particle of thickness delta R. And at steady state, the net number of moles of A that enter the spherical shell at R is given by the expression shown here, where NAR is the flux of A in the radial direction and R is the radial coordinate. There's an equivalent expression for the flux of A leaving the shell at R plus delta R, and then this third term has the rate of production of A due to heterogeneous chemical reaction inside that shell of delta R. And at steady state, in minus out plus net generation has to equal 0 by our shell balance. In the limit as delta R becomes very small, we can replace the delta R with derivatives and get the equation for continuity, in this case that's shown at the top of this slide. In this case, we have to think about the flux and rate of consumption of A, that is capital R sub A, don't have physically meaningful values at a point. They have to be interpreted as values averaged over a small volume in the vicinity of a particular radial location, and that small volume has to be small with respect to the catalyst particle dimensions, that is R, but large with respect to the dimensions of the passages and crevices within the catalyst particle. And we'll show you later how to analyze this more rigorously, but that's the essence of the assumption that we're making at this point. And for the flux, we assume that the analog of Fick's first law governs the mass flux in response to a concentration gradient. So with a two-component system, we're back to the equation we introduced at the very beginning of this section of notes. We'll take a simple stoichiometry, that is A goes to B, and at steady state, there has to be 1 mole of B leaving the catalyst for every mole of A entering the catalyst. So there is the stoichiometry links the flux of A and B together. And so the flux of A and B are equal in magnitude but opposite in sign, since A is coming in and being consumed and B is leaving. We can use the reaction stoichiometry then to simplify the flux expression. So if NAR is equal to minus NBR, then these you have equimolar counter diffusion, and the convection term or frame of reference term goes away, and we're left with this expression for the effective flux of A as a function of the concentration gradient in A. We're writing the diffusion coefficient of A as d sub A rather than dAB to remind us that this diffusion coefficient is not the diffusion coefficient, for example, of gas species A in a mixture of A and B, but rather it's the diffusion coefficient of A, the effective average diffusion coefficient of A, taking into account the porosity and tortuosity of the catalyst particle. This is something that would have to be determined experimentally and would often have an empirical flavor to it. Might be fit to experimental data, for example. And so the flux expression is given here on the left, the mass balance on the right, and if we take in the simplest case that the reaction is first order in A and that it occurs on the catalyst surface area, then we can write that the net rate of generation of A, which can be negative if A is in fact consumed, per unit volume of voids in the solid catalyst particle is equal to the net rate of production of A. Again, this can be negative if A is actually consumed, as it is in this case. And it's the rate of production of A per unit area of the catalyst surface. And then we have a surface to volume term that typically enters these expressions. This little a is the catalyst surface area per unit volume. And this can be on the order of thousands of square meters per gram of material sometimes for high surface area catalysts. But this basically converts the reaction rate on the surface of the catalyst particle to one that will be over the volume of the voids and the solid catalyst, which is what we're writing our concentration in terms of and diffusion coefficient in terms of and flux in terms of, as I explained a moment ago. Again, the concentration here is the concentration of A in the gas phase, appropriately averaged at locally, and you can imagine that there would be, for example, an equilibrium between the concentration of A in the gas phase and that adsorbed on the solid phase where the reaction to B is actually occurring. If we combine these three results, we get the differential mass balance that's shown in the box here at the bottom of the page, and then we need to get some boundary conditions with it. One we've said is that at the outer surface of the catalyst at R equal capital R, the concentration of A is C sub A at R, and that value might be determined, for example, from boundary layer theory. And we're going to require that at the center line of this catalyst particle that C sub A remain finite, that you don't have a discontinuity in the concentration of A at the center line of the catalyst particle. Very typically in solving problems in spherical coordinates, there's a trick you can use that simplifies the problem. So we can change the variable from C sub A to, I'll call it F sub R, which is just R times C sub A. And I'll go ahead and divide by the concentration of A at the outer surface of the particle. That'll ultimately put everything on a 0 to 1 scale for this dimensionless concentration of A. But if you make this substitution in the differential equation, you actually simplify the equation that has to be solved to the form that's shown here. And I'd like you to verify that the solution to that differential equation is the one shown at the top of the page. We, again, as usual, are not typically so interested in the concentration profile itself, but rather in using that concentration profile to calculate fluxes and then to calculate the rate of consumption of A or the rate of generation of B due to chemical reaction. And so the molar flow rate of A or the net rate of consumption of A by chemical reaction we'll write in terms of the flux of A at the outer surface of the catalyst particle times the area at the outer surface of the catalyst particle. And that will give you the moles of A consumed per second, for example. And if the stoichiometry is 1-to-1 with A going to B, then this will also give you the net rate of production of B by the single catalyst particle. We can put the concentration profile, put our expression for the flux in, put the expression, take the derivative using the concentration profile that we have, and you should verify that the result for the net rate of production of A is shown, net rate of consumption of A is given by the expression shown here. It's traditional to compare that rate of consumption of A inside the catalyst particle to what the rate of consumption would be if all the active catalyst surface were exposed to the gas phase concentration of A right at the outer edge of the catalyst. That is, if there were no concentration gradient of A at any point throughout this catalyst particle. And that rate of consumption would be given by the expression shown here, where we've set the concentration everywhere equal to the concentration of A at the outside of the at the outer edge of the catalyst particle. Then this comparison lets us essentially calculate what's called the effectiveness of the catalyst. So we take the actual rate of generation or rate of consumption of A divided by the maximum rate of consumption of A, and that is the definition of the effectiveness factor. The closer this is to 1, the less diffusional resistance there is to mass transfer in the nooks and crannies of this catalyst material, and the more the rate of production of A is just governed by the kinetics of the reaction. The further this value is away from 1 and towards 0, the more restrained the rate of production of A is due to diffusional limitations for A to diffuse into the catalyst pores and for B to diffuse back out. This effectiveness factor depends only on phi, which is the Thiele modulus that showed up in one of the previous problems, and so this is characterizing the rate of dimensionless rate of chemical reaction relative to diffusion. And for non-spherical catalyst particles, I will assert, without going into details, that the results on the previous slide can still be used, provided that the radius of the catalyst particle that appears in this Thiele modulus is replaced by 3 times the particle volume over the surface, external surface area of the catalyst particle. So surface to volume ratio, like in all aspects of transport phenomena, appears throughout mass transport problems as it does in heat transport problems as well. And the absolute value of the consumption rate of A can then be written as shown here. So it's essentially the maximum rate of consumption of A times the effectiveness factor, where the effectiveness factor is given as shown here. And for non-spherical particles, I've replaced phi with this Greek symbol, where R has been replaced as shown up here, but this is effectively an effective Thiele modulus for non-spherical catalyst particles. The reason we write it that way is that you can work out the mathematics in detail for flat particles, long cylindrical particles, spherical particles, and you find that these effectiveness factors versus effective Thiele modulus lie almost on top of one another in universal curves. And so as this effective Thiele modulus gets higher, this indicates faster rates of chemical reaction or slower rates of diffusion, less efficient use of the catalyst in the sense that the chemical reaction is consuming A before it can get very deep into the catalyst to access deeply hidden catalytically active sites. And that's the end of this short section of notes to finish up our discussion of chapter 18. All right, thank you.